Going.
Okay, so the first definition of 3 of geodesics is that they're locally length/energy minimizing, which means, if you have some geodesic gamma, then you pick any 2 points on gamma that are sufficiently close to each other, say gamma of t0, gamma of t1, then the length of the curve gamma restricted to that interval is equal to the distance between those 2 points. And as we know, the distance function is defined to be the infimum of the length of all curves that connect these two. Right. The second equivalent definition is that it's a critical point of the length/energy function. So that means that I'll just write down the mathematical definition real quick. So gamma is our geodesic, and gamma sub s is a family, a 1-parameter family of geodesics, where s is like our variation. So what that means is that, let's say that this is our geodesic, then we have some vector field which is normal to that geodesic, and we have a bunch of curves where the derivative of all those curves is equal to that variation. And gamma is going to be length minimizing in this 1-parameter family, but it's actually going to be length minimizing in all, or not length minimizing, it's going to be a critical point of this energy functional in all 1-parameter families. So sometimes it's going to be minimizing, sometimes it's going to be maximizing. So sometimes it'll be like a saddle point instead of a local minima or maxima. And the third, okay, is that going to last? Okay, good. And the third equivalent definition are that geodesics are straight, or they have no geodesic curvature. So this means that the covariant derivative of geodesic with respect to itself is 0, or if you like, Einstein notation and Christoffel symbols, and we get this just by taking the derivative, applying this DDS to over here, and we get that formula. But the point of the no geodesic curvature is really that the curve doesn't really accelerate out within the manifold at all. So the reason why I wanted to review this is because I wanted to motivate minimal surfaces as a higher dimensional analog of geodesics. There's multiple different analogs of geodesics, but I'm trying to say that minimal surfaces is the correct one. So I really should be saying minimal submanifold, because a minimal, well, I'm just saying surface because the example that I'm going to be talking about is a 2-dimensional manifold inside of a 3-dimensional manifold, so it's a surface. But so a minimal surface / submanifold. The type of object that we're going to be looking at is some function or some immersion from some guy into a larger space, and it satisfies 3 equivalent properties. Locally area / energy minimizing. So what this means is that let D be some subset of our immersed submanifold and make it be sufficiently small. D usually for disk. And let the boundary of this be gamma, which is of course inside sigma, and sigma is of course inside of M. Then the area of this disk is going to be equal to the infimum of the area of S, where the boundary of S is equal to gamma and S is inside of M. So in this sense, the minimal surface, even if it looks a little curved and wonky, every time that I'm drawing a sufficiently small circle around it, minimal surface is actually the smallest possible covering of that loop. The same way that, if we dip a wire inside of a soap solution, we're going to get the smallest possible area. Definition 2, it's the critical point of the area/energy function. So similarly, we take our surface or our submanifold and we look at some variation on it, meaning a vector field that is normal to the surface. And usually we say that it's a compact variation or like a compactly supported variation. But for the minimal surfaces we're going to be dealing with, these are, inside of a compact manifold. So every variation is fine. So we take the derivative with respect to that variation on really all variations. And this is, let's say, U, I guess, d star of n volume on M. So what I'm doing is I'm taking the volume form on the ambient space and I'm pairing it with the normal vector. Since I'm dealing with surfaces in a 3-manifold, these are hypersurfaces. There's only one normal direction, right? And really what this is just doing is just changing basis, like the same way that if you write the volume form as dx1 through dxn, and then I want to write it as dy1 through dyn, well, then I have to put something out in front of here, which is going to look like partial xi, partial yj, and the determinant of that. And that's just the change of basis thing. So this guy right here really just looks like the determinant of this thing called the second fundamental form. And what that is, well, it looks pretty much just like this, except a little bit more geometric. This is going to be the inner product of, or how do I erase? Where is it? Yes, good. Let's say the ijth component of this is going to be, you just take the covariant derivative of the ijth directions, and then you take the inner product with n. So it's pretty much the same thing when we take the determinant there. And the last equivalent definition is that minimal surfaces have zero curvature, let's say. Except that's not exactly correct. So I should really say zero mean curvature or zero average curvature. Now, what do I mean by that? Okay, thank you. Well, the best way to see that would be to, or the way that you would normally do in a geometry class would be to take the variation of this and of this formula up here and try to find what pops out. we're not going to do exactly that because I want to avoid doing any real analysis in this talk. But you can just think of, we're taking a derivative here, and there's a determinant. And you know that the derivative of determinants are traces. So having zero curvature is the same thing as saying the trace of the second fundamental form is equal to 0. And this guy is defined to be, or we call this H, the mean curvature. Okay, so what does that mean? No pun intended. What that means is, if you look at the second fundamental form here, we have the covariant derivative of partial I and partial, with respect to, covariant derivative of partial J with respect to partial I, right? So if we have some minimal surface here, and we have our two coordinate directions, the I direction and the J direction. Well, if we look at a curve that's going exactly here, that's horrible. If we look at a curve like this, and we say that gamma dot is equal to partial I, then the ith term of the second fundamental form is really just the geodesic curvature of gamma in a product with n. Now, I shouldn't really be calling this a geodesic curvature because my advisor Marcus would get upset at me. Technically, this is the geodesic curvature of gamma inside of the ambient space, M, but this is just what's called the normal curvature. It is the curvature in the normal direction to our submanifold. Makes sense? We're taking the inner product with the normal vector. So to say that the mean curvature is 0, or to say that the trace of the second fundamental form is 0, that means that in some sense, the average of all of these normal curvatures is going to be 0. So sometimes the curve is going to be, curving too much in one direction, and sometimes it's going to be curving too much in the other direction. So sometimes if I take a geodesic in the ambient space that starts off in the partial I direction, it's going to be going off the surface like this. And sometimes when I do it in the other direction, it's going to be going below the surface. Trying to draw in 3 dimensions. Didn't work. But that's fine as long as they cancel out in the end. And the sum of all of those curvatures is going to be 0. Are there any questions? Okay. So now let's move on to looking at minimal surfaces in the 3-sphere. So the most obvious minimal surface is going to be the equator or the equatorial sphere, right? Now, we kind of know that this is going to be a minimal surface just from symmetry, just by basically looking at it. But you might think that it's weird to call this minimal since it's not actually energy or area minimizing. I can always just slide the surface closer to one of the poles and get smaller area. But really, this guy in the middle is the largest area surface in this one parameter family. But if I were to do any other variation, so let me draw this again. So this is our equatorial sphere. If I'm going to do any other variation on it, like maybe this small bump here, we can see that this surface is going to have larger area if I'm performing these variations, which means that the equatorial sphere here has the smallest possible area. And then there's another variation I could do, which would be if I'm just rotating the entire sphere. And technically, this variation doesn't change the area at all. They all have the same area. They're all equatorial spheres because of symmetry. So we tend to just ignore this one. And I mean, it doesn't really do anything. The derivative in this direction, the change in area with respect to this variation is going to be 0 anyways. So, the equatorial sphere is still going to be a critical point. What we can do is say it's a saddle point and count the number of dimensions that it's maximizing over, which in this case is just one, just this guy. So we say that the equatorial sphere has index 1. Or whatever. And index is equal to the number of dimensions that the minimal surface is actually maximizing area over. In all other dimensions, it's still going to be minimizing. So, it's a saddle point, but with finitely many negative eigenvalues. And the reason that the index is always going to be finite is because basically the Laplacian is an elliptic operator, but that's analysis, which I'm not going to be talking about. So the way that people see that this equatorial sphere is minimizing is, there's two ways to do it. One is the hard way with analysis, is to look at a sphere and to then look at all possible sweep outs of the sphere. Basically, we foliate the sphere, the 3 sphere by 2 spheres. Hold on. Okay, cool. Basically, we foliate the 3 sphere by 2 spheres. And in this foliation, we find the maximum. The maximum area 2 sphere. That's usually the one in the middle. And then we look at all possible foliations. And so, and then the this critical point is going to be the, let's say the max, I don't know how to call this. Whatever. I was trying to erase with the thing. Is going to be the max area surface inside this foliation. And then it's going to be the minimum area surface over all possible foliations. And that's what's called the minmax method. And that, it's a very powerful technique. It can get you lots of minimal surfaces. However, they typically have some problems. One, you have to deal with regularity. And two, the surfaces that you get in the end are usually not embedded. They're usually immersed. Oh, that's right. The way that we're going to be dealing with this is to use symmetry because we have the round 3 sphere, so that's a lot easier. So that brings us to a theorem. If F, an isometry, has a fixed point set, then N is totally geodesic. So totally geodesic is actually much stronger than minimal. What this means is that if you have a totally geodesic submanifold, then at every point in your submanifold, if you pick any direction in that in the tangent space of that submanifold, if you have a geodesic in the ambient space that is tangent to this surface, it's going to stay entirely inside of N. Or in other words, if gamma is a geodesic in N, then gamma is also a geodesic in M. Or lastly, geodesics never leave the submanifold N, which means that this quantity is going to be 0 for all directions. That's fine? Okay. Which means that this quantity is going to be 0 for all directions, or the second fundamental form is just identically 0, which is a lot stronger than saying the trace of the second fundamental form is 0. So to show that the equatorial sphere is minimal surface, all we do is we take the reflection symmetry. Which obviously has a fixed point set of this equator. So boom, we found our one minimal surface, or our first minimal surface. Okay, so now we want to find some more complicated minimal surface. The more complicated minimal surface that we want to find is called the Clifford Torus. Yeah. And Lawson has a conjecture about this, or had, it's since been proved. The only minimal surface of embedded. Okay, sorry. Minimal surface of genus 0 embedded implies the equatorial two-sphere, the one that we just showed, and an embedded minimal surface of genus 0, and then an embedded minimal surface of genus 1 is the Clifford Torus. And that's it. This is the equatorial two-sphere is the only embedded minimal surface of genus 0, and the Clifford Torus is the only one of genus 1. So in order to see what this Clifford Torus is, we're going to first go towards the Hopf action and the stereographic projection. So which one do I want first? Yeah, let's talk about the Hopf action first. So we want to think of the three-sphere as sitting inside of C2. So this is the set of ZW such that the norm of Z squared plus the norm of W squared is equal to 1. Well, the Hopf action is just using the diagonal circle action on C2, or rather the circle action on the first C and the circle action on the second C. So you just go e to the I theta times Z, e to the I theta times W. Now, this is a rotation in R4, which is an isometry in R4, so it's clearly an isometry on the unit sphere as well. And or the difference between this isometry and the previous one is that this one has no fixed points. So we're not going to be using this, isometric action to find any minimal surfaces, at least, or to find any totally geodesic submanifolds. However, it is still a very important action, so let's try to visualize it by using the stereographic projection, which, recall the stereographic projection in like 2 dimensions less. You just take your sphere and you bisect it by the plane, and then you look at lines that go from the North Pole to the plane and where they intersect. I should make that way larger. Sorry, I'm still not used to this. Where they intersect the sphere, this point gets projected. This point gets projected down to this point. We don't really need to know about the metric for the round 3 sphere on R3, but if you really want, it looks, I believe, like this. So it's clearly spherically symmetric. R is obviously the radial direction. Yeah, the only thing that you need to know about this is that the conformal factor in front of the metric depends on the position. The closer you are towards the center, the larger. Yeah, the larger this quantity is, the further away from the center, the smaller this quantity is. Okay. Anyway, so let's look at the stereographic projection. So what it's really doing is it's destroying the complex, or the purely imaginary value of this last term. So a circle in just the second C direction, basically something of the form, is going to project down to a vertical line here, the z-axis. And then a circle in the first C direction is going to project down to the unit circle in the xy plane. And both of these are geodesics because, well, we can think of these guys as the fixed point set of a rotation isometry. Well, actually, it's a lot easier to see. Sorry, that this vertical line is a geodesic using this metric. So we can see that there's a rotation about this vertical axis that doesn't change the metric, so it's an isometry, and the fixed point set of any isometry is a geodesic. To show that the image of this guy is a geodesic, we can apply a rotation to this, another rotation. Let's say that we have a rotation which takes a rotation which takes where is it? Okay, yeah, sorry. ZW gets sent to cosine phi z plus sine phi w, and W gets sent to minus sine phi z plus cosine phi w. So this is just a rotation of the two complex planes, which is an isometry in R4. So it's going to be an isometry on S3. Now, if we take this guy and apply this rotation to it, this is sent to z is 0, so it gets sent to sine phi e to the I theta cosine phi e to the I theta, which in the stereographic projection, basically we destroy the purely imaginary part of this, and this guy gets converted to the x and y part. So if we let theta, sorry, yeah, if we let not theta, b be equal to pi over 2, then this is just going to be, e to the I theta, 0. And then when we go down to the stereographic projection, this is just going to the x and y coordinates, and we get this nice hula hoop around the z-axis, which, since it's an image of another geodesic through an isometry, this is also going to be a geodesic. All right. One other really important thing to note is that this guy looks like the image of, or the orbit of, the point sine theta, or sorry, sine phi, cosine phi through the Hopf action. And, or yeah, this, let's say, the set of points sine phi e to the I theta, cosine phi e to the I theta for a fixed phi. This is going to be the orbit of a single point in the Hopf action, but it's also going to be a geodesic. So we have isometric action whose orbits are also geodesics, which is quite rare. Now let's look at what these orbits actually look like. Well, we know what two of them look like. We have the vertical line, and we have this hula hoop. What the others look like are going to be, well, they're basically curves which come out like this. Under, so then this is going to go over. I can't erase like that. Shit. I can't erase just part of a curve, can I? Okay. Forget that. The real way to see these curves is actually to take rotations about the z-axis anyways. So I'm just going to skip trying to draw the curves individually and just draw it like that. So we're going to take the curve and try to do a rotation about it. So we should know what kind of shape we're going to get in the first place, because these are orbits, and orbits can't intersect each other because this is an honest to goodness fiber bundle. S1 going down to S3, there's no fixed points here. Or S1 acting on S3 with no fixed points. This is an actual fiber bundle, so the orbits don't intersect. Each orbit is going to be an S1, and I'm rotating about the z-axis, which means that we're going to be getting an S1 cross an S1, which is a T2. Now, the orbits of the Hopf action look like curves on this, like this. I'm obviously cutting the this torus in half, just so that we can see it a little bit better. It would be a full torus. So they look like curves like this, going from the outside edge here to the inside edge. And there's going to be, lots of different tori for every point in here. Basically, there's going to be a foliation of tori for this 3-sphere, where there's going to be 2 trivial tori here in the center, this single 0 width hula hoop, and then this vertical line 1. Yeah, I can try that. Yeah. And each tori is actually foliated by these curves, which are geodesics. And when a manifold or a submanifold is foliated by geodesics like this, it's called a ruled surface or a ruled submanifold. Meaning that it is so. What does that mean in relation to a minimal surface and a totally geodesic surface? Well, minimal surface means that if we look at these curves going out from here, and we calculate their normal curvature, their average is going to be 0. And since the normal curvature is going to be a real number and they're averaging to 0 by the intermediate value theorem, we know that there exists some basically curve coming out of here with 0 normal curvature. This is a minimal one. And then totally geodesic means that every single direction there's going to be 0 normal curvature. And a ruled submanifold, I know I'm drawing the exact same picture each time. And a ruled submanifold just means that there exists a single direction, but at every point. So we have like a ruling of lines, like ruled paper. And in this direction, we have 0 normal curvature because these are actual geodesics. So a ruled surface is weaker than a minimal surface, which is not exactly what we want yet. We want a minimal surface. However, this guy has some extra properties. One, this hop action relied on some choice. We have another equivalent hop action, which is basically the conjugate action. Or you want to think about it another way, we're just going to be reflecting about this this plane, not about the vertical axis, let's say about the ZY plane. So since it's an isometry, the image of every geodesic is going to be a geodesic, which means all of these lines on the torus get reflected. Was it one notes or notes? Good note. Okay, sorry. Which means all of these lines get reflected. And we have actually a double ruling. Now, this still isn't enough to show that these tori are minimal surfaces. In fact, they're not. Not every single one of these tori are going to be minimal surfaces. But we do know a little bit about all of these tori. We can talk about what they look like inside of R4. Hold on. Yeah, each of these tori, let's say T2 theta, is going to be the set of ZW such that norm of Z is equal to cosine theta. The norm of W is equal to sine theta for a fixed theta. As you can see, when theta is equal to 0 or pi over 2, one of these two terms, the Z or the W, is always going to be 0, and we're going to get just a single circle. But whenever theta is some other value, both Z and W can live, and we have a two-dimensional surface. Oh, also, sorry, this is the set of these guys equal to this, which is inside of S3. And obviously, norm of Z squared plus norm of W squared by the Pythagorean theorem is going to be 1. So this T2 is really just the product of two different manifolds. This is just the product of S1 of radius cosine theta and S1 of radius sine theta. It's an actual Riemannian product. The W and the Z have literally nothing to do with each other in this definition. And whenever we have the Riemannian product of something, we can look at the curvatures of this guy and this guy to find the curvature of the total space. Fortunately, one manifolds are always flat. There is no curvature or no intrinsic curvature in any one manifold, which means that all of these tori are flat. Now, we've seen pictures of flat tori before. They're just, rectangles where you identify the sides in a certain way. And we have a ruling on these flat tori. The ruling are just these diagonal lines. How did that happen? Okay, just these diagonal lines, right? And a double ruling. And all of these are straight lines or geodesics. Now, some of these tori are going to be really long and skinny, or short and fat, and some of them are going to be tall and skinny. Right? But for all of them, they're flat and homogeneous, and thus the angle that all of these curves meet at each other is going to be exactly the same. Now, at one extreme, this angle is going to be, 0, and at the other extreme, it's going to be pi. So by the intermediate value theorem, we know that there exists a torus in the center where all of these rulings meet at exactly pi over 2 or 90 degrees, or right angles. And of course, by symmetry, we know that it's going to be the middle one because, well, we can flip it on its head. So, almost done. Yeah, this means that there exists a torus in the center where these meet at 90 degrees. This is called the Clifford torus. And the way that we see that this Clifford torus is actually a minimal surface as opposed to all of the other ones, well, we go back to the definition of minimal surface involving mean curvature. Basically, it's saying that the average curvature is going to be 0, right? Well, let's think of the second fundamental form as a quadratic form. And then let's look at the graph of this quadratic form. So the graph of a quadratic form is going to be, some saddle. I mean, it could be a parabola or actually that's it. It could just be a parabola or a saddle, but I'm going to draw a saddle because, that's the answer. And I'll show that. Okay, so because this has a ruling on it, that means that we know that at every point, say the center point, well, actually, that's whatever. At every point, there's going to be a geodesic, and geodesics have zero curvature. And in the other direction, there's also going to be a geodesic, which again has zero curvature. So we have a quadratic form where we know that there's two directions where this guy is going to be zero, and we know that they're normal to each other. So this guy, I mean, it clearly can't be a paraboloid, otherwise it would be identically zero. So we know that it's a saddle. And since it's a saddle, we know that between two of these points, this B and W, everything is going to be negative. Down here on the other side as well. And above them, they're going to be positive. What we're really trying to do is we're trying to find the eigenvalues of this quadratic form, which is going to be, the value in this like minimal most direction and the value in this maximal most direction. Well, because these two meet at 90 degrees, we know that there's a symmetry here, and that basically we can reflect the entire, or reflect and rotate this entire saddle on its head, and we get that these are the two eigenvalues, and they exactly cancel out. Or those aren't the two eigenvalues, those are the two eigenfunctions, whatever. But it's quadratic form, whatever. And therefore, the trace of the second fundamental form is going to be zero. I mean, curvature is zero. And the Clifford torus is indeed a minimal surface. And that's exactly time. Okay. Sorry for all the technical difficulties and everything else. That's it. Anybody have any questions?
Jordan?
Yeah.
So earlier you had something about inside of S3, you're looking for these minimal surfaces with some genus. What happens for higher genus?
So the way, sorry, are you asking how we know, or how the genus 1 is being used in the proof that the Clifford torus is the only one, or are you asking for examples of higher genus guys?
Oh, I'm just asking if is there a similar classification?
Okay. Not that I'm aware of. I don't know if there is a similar classification or like rigidity statement in higher dimensions. I know that a lot of examples of minimal surfaces are basically you take existing minimal surfaces like the Clifford torus. Let me just draw that again. And then you take a second Clifford torus, or I mean, neither of them are the Clifford torus. They're both slightly perturbed from the Clifford torus. And like, let's put it, directly inside. And then they cut holes in these two guys and attach them together by catenoids, which are the minimal surface in Euclidean space that looks like this, the nuclear exhaust tower thing. And they cut lots of holes and attach them like this. And then they show that the minimal surface, the mean curvature of these guys is very close to 0, but not exactly 0, because, because they had to glue them, and the gluing made them a little bit off from 0. And also, neither of these two guys were actually Clifford Toruses. But then they show that there's a mean curvature flow on this surface, or an inverse, regular mean curvature flow on this surface actually converges to some object, which, because of all these holes cut in it, has a very high genus. And they can do this. I think the genus grows like k squared or something like that. So not literally every genus is achieved in this way. I think there's another way to get minimal surfaces using minmax method and sweep outs, and there you can get some other kind of genuses, basically by taking a non-standard Heegard splitting of the 3-sphere. So instead of like just viewing it as two solid balls glued together or two solid tori glued together, maybe you can think about it as two solid genus 2. I'm not sure if that one works, but sure, two solid genus 2 tori glued together, and then do some sort of like min-max thing there and get something of genus 2. Don't quote me on genus 2, by the way. I think genus 3 works though. Are there any other questions?
Yeah, okay. I'm not sure if you mentioned this, but how can you see from your construction that the Clifford torus is actually S1/2 cross S1/2?
Is actually S1 of 1/2 radius across
Yeah.
S1 of half. Yeah. So let's see. Did I mention that? Yeah, a lot of my stuff wasn't very rigorous. I apologize. So we know that this guy is like a flat torus, and there's a different. Oh, am I not sharing anymore? What's going on? No, I'm moving the screen and it's not moving. No, it's not.
Okay, no worries. Just explain.
Okay. Sorry.
Yeah.
Anyways, the basically by a reflection. Like I said, that we know that there exists something in the middle by using the intermediate value theorem, right?
Yes.
However, the better way to do it is to just say that we have this symmetry, that we can move this vertical geodesic to that hula hoop geodesic by doing one of our rotations, like that rotation on C2, which switches the two complex planes to each other. That will switch this geodesic to this geodesic entirely.
Okay.
And that is an isometry, right?
Sure.
So if the Clifford torus was like in the first half of this foliation, then we do the isometry and we get that the Clifford torus is actually in the second half. But we know there's only going to be one, so it has to be exactly halfway in the middle.
Okay.
So basically, just by isometry, it's not the fixed point, but it's the thing in the middle.
Sure. Okay. Thank you.
Any other questions?
Yeah. So, what is the intuition for Lawson conjecture? So, why is the Clifford torus is a unique minimum surface with genus 1?
So, for a while, the equatorial 2-sphere was the equatorial 2-sphere was the only one known. Then they found the Clifford Torus, and then like that lasted a long time before they found any other minimal surfaces. And the next batch of minimal surfaces were all immersed genus 1 tori. They weren't embedded anymore. So it could have just been that they didn't find any others and they really didn't think there were. It's also that, I mean, the equatorial two-sphere is totally geodesic. Like we get it immediately by symmetries just by doing this reflection. But as my talk showed, the Clifford Torus, it's not immediate, but it is still very rigid and it's very much gotten by symmetries. You know, we didn't use any calculus to show that this is a minimal surface other than the definitions of minimal surfaces themselves, right? We have this double ruling, which forms 90-degree angles, and that gives it like some extra rigidity. Now, in the actual proof that the Clifford Torus is the unique one, this was, I think, done by Simon Brendel, and he uses some complex analysis, actually. Basically, since the torus, or since all surfaces are, you know, two-dimensional, and in two-dimensional Riemannian geometry, they're all, you know, conformally flat. Basically, we can, you know, it's just some factor times like the Euclidean metric, right? So he basically looks at the mean curvature, or yeah, I think it's the mean curvature. No, the second fundamental form, sorry, as the pullback of something from the three-sphere onto the complex plane, and then uses what is it? Frobenius theorem, Poincaré's theorem, the thing that says that holomorphic functions, if they're bounded, are constant. Basically, which one is it? Okay, yeah, maximum principle, but it has a name in complex analysis. Louisville's theorem, thank you. Yeah, so he uses Louisville's theorem to basically show that that because this function is holomorphic and it's bounded because, you know, it's coming from, like, the domain is either a two-sphere or a T2, which is a compact closed domain, that the second fundamental form is going to have to be 0, or the trace of it's going to have to be 1. Anyway, he uses something like that. And then there's another part of the proof that I don't understand at all, but I can give you the paper.